Hi there, welcome to this talk. My name is Nico Galoppo. As part of the Intel OpenVINO developer tools team, I work with our customers to improve the performance of their AI use cases. More often than not, their use cases include high performance processing outside of AI, and often that processing can be accelerated with SYCL code. This talk is all about making sure that not only the AI and SYCL parts are optimized, but also the entire end-to-end, so that it can run as fast as possible. Some great examples of complex AI pipelines can be found in the Internet of Things world. Robotics and smart cities are just two examples shown here, where people fuse together the perception of multiple types of sensors to create the most accurate understanding of the environment. Decision-making and planning use that understanding to decide on which action to take. On the sensing side, we see that LiDAR and radar have become essential to complement traditional RGB-based cameras. They typically output sparse point clouds, as opposed to the regular grids of pixel data coming out of RGB cameras. Due to the different types of sensor input data and fusing of information, each one of the compute components are becoming increasingly demanding in terms of compute needs. Deep learning and data parallel compute are important to achieve the target accuracy and response latency, and so this is where OpenVINO and SYCL are relevant. Point pillars is one of the go-to workloads for point cloud processing in the industry. This is the compute pipeline we'll be using as an example today, and the one we'll be optimizing as a case study. Point pillars has become a standard model for object detection from radar and LiDAR. Beyond object detection, point pillar is also often used as the encoder for semantic segmentation, classification, temporal detection, and tracking in point cloud inputs. This model is different from typical AI processing, where a single deep learning model is being inferenced from input to detection. Rather, the point pillars pipeline is a mix of general data parallel processing and deep learning inference stages. With point pillars, one must shift compute from a deep learning inference engine to a data parallel compute engine, and vice versa. The deep learning engine that we'll be using today as an example is OpenVINO, and the data parallel compute API is SYCL. Since there is a back and forth data flow between different APIs in a workload like this, it is not only important to optimize the individual compute stages, it's also essential to optimize the entire end-to-end pipeline. So what are some of the key inefficiencies that could exist in a mixed pipeline, beyond the inefficiencies of its individual components? Let's look at a hypothetical example. Here we have a timeline of compute on a host and an attached accelerator device, with their memory represented in between. Let's imagine a pipeline with some SYCL and deep learning work. First, the input data is processed by SYCL, and the output is then processed by the deep learning engine to produce the final result. In this example, the host doesn't do any real work. It only schedules the device-side work with SYCL and deep learning APIs. Data flows between the host and the device memory as needed. Now we can clearly see that there are some potential inefficiencies in the implementation. First, as implemented here, a round trip of the SYCL output data to the host memory is needed to feed back into the deep learning engine. Second, the application invokes explicit waits on the host thread to wait for device work to be done before scheduling dependent work. As you can tell, these inefficiencies lead to lots of idle time on the acceleration device. Let's see what we can do to optimize the data flow and make sure we maximize device utilization by always keeping it fed with work. The first thing we can do is remove unnecessary copies of data. What if the output of the SYCL processing can be directly ingested by the deep learning inferencing stage? We could do that if the APIs agree on a common representation of the memory, also referred to as memory handles. So what is the result of pointing to the same memory from both APIs? It is now clear that this can significantly reduce the idle time and increase the utilization of the device. So great. However, we're not done here. There's still some idle time due to the explicit wait between API calls on the host thread. How can we solve that? Well, If we can somehow signal to the device that the inference stage is dependent on the completion of the SYCL stage, then the host doesn't need to wait for the SYCL stage to be finished before scheduling the inferencing stage. The way to do that is runtime and backend specific. Our solution relies on using a common device work queue, or alternatively, a common concept of events between the APIs. For example, if the host thread can schedule a barrier that signals to the device work queue that the SYCL work needs to be complete before the deep learning work can start, then we can completely avoid the idle time on the device. Awesome. This looks much better. If you haven't noticed yet, there's a pattern here. For us to apply these optimizations, it is essential that the APIs can talk to each other, that they can agree how to point to the same memory, and that they can agree on synchronization concepts. That is what we call interoperability, or Interop for short. So now that we understand what we're trying to do, let's look at how we can do this in practice with SYCL and OpenVINO. Let's have a brief look at these two APIs and some of the concepts that we'll be relying on. First, there's SYCL 2020, which I'm sure the audience is very familiar with. This version of the standard has introduced the concept of compute backends, extending beyond the previously supported OpenCL backend and expanded interoperability with those backends. It also introduced the concept of unified shared memory, also known as USM, which we will rely on in our solution. Unified shared memory enables consistent pointer values between host and device, a feature that is achieved through unified virtual address spaces. And that's exactly the type of common memory handles that we were looking for earlier. For deep learning inference, we're using the OpenVINO inferencing engine. OpenVINO is an open source deep learning toolkit that supports multiple device types with a plugin design. And just like SYCL, certain plugins support multiple backends. For example, the GPU plugin supports OpenCL and Level 0 backends and can work with unified shared memory allocations as well as OpenCL buffer types. More about that later. Most importantly, the OpenVINO API has methods to schedule inference asynchronously. That avoids blocking the application thread and will be important when we optimize synchronization between API calls. The tools we'll be using in our optimization case study rely on the interoperability APIs in SYCL and OpenVINO. Interoperability in SYCL is defined with respect to the backends it supports. Today there are backends for OpenCL, Level 0, CUDA, Vulkan, and others. On one hand, native backend objects can be retrieved from the SYCL object. This allows for using the native APIs such as OpenCL in a SYCL program. For example, to get the native OpenCL command queue from a SYCL queue to enqueue an OpenCL-based library function. That's exactly what we'll be doing today. On the other hand, it is possible to use part of the application written in SYCL from another part of the application using another API by constructing SYCL objects like a SYCL device or a SYCL queue from native equivalent objects. SYCL 2020 has a few other interoperability features that are out of scope for this talk. If you're interested, definitely check out talk 139 at this conference that goes in depth into this topic. On the OpenVINO side, interoperability is also defined with respect to the compute backend. It is abstracted using the remote context and remote tensor classes. The remote context wraps the native backend context, for example an OpenCL context. This object can be created from an existing native backend handle, as shown in the example code, or a default context can be retrieved from the runtime plugin. The remote tensor is an abstraction to wrap native backend memory handles, such as unified shared memory pointers or OpenCL memory handles. The examples show how to create a remote tensor object from an existing unified shared memory pointer within the remote context. Remote tensors inherit from the standard OpenVINO tensor class, and so they can be used in all OpenVINO APIs that take a tensor. The most important example here is a standard inference request call. This is great because the SYCL API also supports unified shared memory handles. We'll use unified shared memory allocations to share data between the two APIs. Alright, so how do we go about and build a pipeline that uses the concepts that we just discussed? Here's a generic recipe you can follow to apply these optimizations. The basic principle and main requirement for interoperability between SYCL and another API is to use a common backend. Here we will use OpenCL as the common backend. But for example, if your API doesn't support OpenCL but does support, say, level 0, then you can use that. We can use the SYCL device filter environment variable to force SYCL to pick a specific backend and a device that supports that backend. The first step in our recipe is to create a remote context from the SYCL queue. You can follow along on the right to see the code on how to do this. We first use the SYCL Interop API to get a handle to the native OpenCL queue, and then we use the OpenVINO Interop API to create a remote context from that queue. This ensures that SYCL work and OpenVINO inference will all be performed on the same device work queue and in the same context. From there, we compile the deep learning model for execution. We tell the OpenVINO inference engine that we'll be using OpenCL for execution. Next, we allocate unified shared memory for the inference input and output memory. We do that with a SYCL malloc APIs. In this case, we allocate device memory, since that's where we want the data to reside, but host side or shared allocations work too. We also wrap these input and output pointers into OpenVINO remote tensor instances with the create tensor methods of the remote context object. That allows us then to assign them as inputs and outputs for the deep learning inference. Remote tensors inherit from the OpenVINO tensor class, and so these are standard OpenVINO API calls. They're not specific to the interop functionality. As you can tell, we still have an explicit wait call on the bottom of the application code. Instead, what we want to do is to move this host-side synchronization to the device. For OpenCL, we can do that using the enqueue barrier API. Note that we do have to use the native OpenCL API, which is not ideal, but it works. So there we go. That's all that there is to it. Steps 1 through 4 can easily be done at application startup. Only the last 2 steps are part of the main application loop. Okay, so let's put all this theory into practice and look at optimizing our point pillars implementation. We're starting from an open source implementation for which the link is provided in the bottom of the slide. Here's a simplified view of the point pillars processing pipeline. The green blocks are SYCL processing, and the blue blocks are deep learning inference with OpenVINO. We want to make sure that we optimize the transition between each stage. That means sharing SYCL outputs with OpenVINO inputs, sharing OpenVINO outputs with SYCL inputs, and removing waits on the application thread. Let's focus on the 3 middle stages highlighted here. Look at some real performance data, optimize each step, and look at the before and after. Here's a typical timeline we captured of those 3 stages, and that is before optimization. This was captured and visualized with the vTune profiler. So first let me explain a bit what all these bars and colors mean. In the middle of the graph we have an illustration of tasks on the application thread. You can already see specific OpenCL API calls that may be familiar to you. These API calls were issued by the higher level SYCL and OpenVINO APIs. The red bars on the top of the timeline indicate work that is being performed on the device. In this case, it is a Intel integrated GPU. And then finally on the bottom in yellow, we have a graph that represents the percentage of GPU utilization. Dips in this graph indicate time slices where the GPU is idle, meaning it doesn't have any work to do. So now let's overlay our pipeline stages over this timeline. As you can tell, there's quite a bit of time spent between these stages. There's some good opportunity for optimization. For example, on the right side, there's about 2.5 milliseconds spent in copying the scatter output buffer to inference input memory, and a smaller amount of time spent copying memory on the left side. There are also explicit waits on the application thread. For example, the application is waiting for completion of the scatter stage before scheduling the subsequent inference stage. This is causing idle time on the GPU. Finally, there is also some good time spent clearing an input buffer. Unfortunately, we can't get around this cost. In all, this represents a 5 milliseconds chunk of our pipeline. Let's see if we can bring that number down. As a first step, we will share the scatter output memory with the inference input. On the left is the code before optimization. We're not using any interoperability between SYCL and OpenVINO just yet. DoScatter is a function that calls SYCL APIs with unified shared memory pointers as input and output. Notice that we are copying the scatter output to the inference input with a call to memcopy. On the right is the optimized code. And in the code comments, we're referring to the steps of the recipe we discussed a few minutes ago. I hope it's clear that aside from the initial code setup to create remote context and remote tensor instances, there isn't much changing to the code. We remove the memcopy call and replace it with a simple assignment of the wrapped unified shared memory pointer as the input for inference. So here's the picture again before the optimization, with a huge red copy block on the right. And here's the picture after, as measured again with our profiler. As you can tell, the memory copy is gone and giving us 2.8 milliseconds of savings. Great! So let's continue. As a second optimization, let's share the first inference output as an input to the scatter stage. On the left is the before code. Here again we have an explicit memcopy call. On the right, we apply steps 4 and 5 from our recipe again and remove the memcopy call. Seems easy enough, right? And let's see what that does. Here's the before with the red copy buffer block after inference on the left. And here's the after. The copy block is gone and we saved another 150 nanoseconds. We did well so far, but can we do better? There's still quite a bit of idle time on the GPU timeline. Remember, that's due to explicit waits on the application thread. Those wait calls are highlighted here in the code on the left. The first wait call is actually an OpenVINO API on the inference request object. The second wait call is a SYCL API on the SYCL queue after the scatter phase. Now remember that the SYCL and OpenVINO runtimes have the same OpenCL command queue in the backend. That means that we can schedule a device-side barrier on that queue by using the OpenCL method for enqueuing barriers on a command queue. That removes the need for waiting on the application thread, because the device queue now knows that it should not run scatter before the first inference ends, and that it should not run the second inference before the scatter ends. Let's look at the impact of our optimization. Once more, this is the timing profile before optimization. Note the purple CL finish and pink CL wait for event calls on the application thread. You can also see that the application only schedules subsequent work until after the previous work is done. You can tell from the brown CL and QND range calls. And here's a picture after our optimization. The waits are gone. The yellow GPU utilization bar now shows 100% utilization at all times. You might also wonder where the enqueue calls went. Well, they've all moved to the beginning of the frame, entirely outside of our picture here, because effectively the application was able to schedule the entire pipeline on the device without having to wait for any of the actual work to be done or even start. Great. So we were able to decrease the original 5 milliseconds between both inference calls to about 1.5 milliseconds. Not bad, considering we didn't optimize any of the actual compute work. We only optimized the handover of the work between the APIs. In closing, I'd like to spend a few minutes touching on the design and implementation of OpenVINO's Interoperability API, in the hope that this can help other API developers to create their own interop with SYCL. The remote context and remote tensor classes are abstract-based classes that were intentionally kept very generic, independent of the OpenVINO runtime plugin or the compute backend it is using. These interfaces can be implemented by any OpenVINO plugin and can provide interoperability with any compute backend imaginable. Currently, only the OpenCL interoperability is supported by the GPU plugin, with level 0 support planned for. OpenVINO doesn't require you to share the context and queue with the external API, but there are advantages of doing so. The most important one was showed today is that it lets you schedule the entire pipeline from the host without blocking the application thread in the middle of the pipeline. However, it does come with a limitation. The OpenVINO runtime can sometimes achieve higher inference throughput by scheduling work on multiple concurrent device queues. This is also called throughput mode. That optimization is not available when you compile a model with queue sharing as we did today, because it could effectively only use a single queue. Another limitation of OpenVINO's Interop API is that there is no native mechanism to synchronize the pipeline on the device side or to specify work dependencies. We showed that we could work around this limitation by inserting a barrier on the native OpenCL queue, and that works, but it is kind of a crude solution. It would be nice to be able to express more fine-grained dependencies between tasks. The OpenVINO team doesn't currently have plans to add such functionality, but we do have some ideas about what the API could look like. So here's what we've been thinking. The code snippet here shows the OpenCL and queue barrier calls we'd like to replace. And one idea would be to add direct support for SYCL event types. And that works, but it's really not that flexible, since each inference plugin would then have to support SYCL in addition to the actual backend API. Instead, we follow the pattern of the existing OpenVINO Interop API, and so we abstract events with a remote event object that wraps the native backend event type. We also expand the OpenVINO inference request class with a new method that can take a set of dependent events as argument and returns a completion event. With that in place, we can replace the original code with the new code here. We first turn the SYCL completion event returned by the scatter phase into the native OpenCL event type, and then we wrap that into a remote event instance. This event instance is now a dependency for the inference request, so that the runtime can include that dependency when it schedules the inference through the device backend. The inference request also returns a completion event, which can be used directly as a dependency for other inference requests, or turned into an OpenCL event to become a dependent event for future SYCL calls. That brings us to the end of this talk and to our call to action. I hope that I have convinced all of you of the value of interoperability with SYCL for optimization of mixed API pipelines. And if you're a developer of another API that might coexist with SYCL in data processing pipelines, then I hope that this talk encourages you to add interoperability to your API too. There are a few lessons to be learned from our experience in OpenVINO for other API developers interested in adding Interop with SYCL. First and foremost, lean on a common compute backend. That could be OpenCL, Level 0, or any other backend supported by SYCL today, and depending on what your hardware supports. Second, avoid including SYCL into your API explicitly. Instead, provide abstractions for compute context, memory handles, and sync objects. That provides maximum flexibility to your API, since your API doesn't need to speak SYCL, only the backend API that you're probably already using. It also provides extra flexibility to the users of your API, since this approach naturally extends to providing Interop with programming APIs beyond SYCL. So that concludes my talk. Thank you for listening, and please send questions and comments via email or reach me on Twitter. Thank you.